So welcome everyone on Sunday's meeting. Today we have a special guest, Pierre-Luc St.Charles. I can say that he is a Canadian and he's a scientist in, let's say, computer vision realm and all that's underneath it. Is it right to say so? Okay.
Yes, that is correct.
So this is a session of today with a special guest where we hear and try to learn from your experiences so that we can improve what we do and maybe get new directions where to head to. And we have a lot of questions, and we only put the seven main ones, let's say. But there are hundreds
It's
more.
Good ones, so that's very nice.
You have to say stop, okay, when you say stop, otherwise it could take hours. So it is supposed to take just 1 hour. And we'll just give you a short introduction about what Sky 360 is. So, heck, here, show, and share screen. And there we are. I hope you can see a blue Sky 360 logo on white Sky 360 on a blue screen. Okay. So our main goal is to establish a network of roughly 150,000 measuring stations that are autonomous and have a sensory equipment that works 24/7 to give us a 24/7 permanent sky awareness about all there is around our planet. The idea with the 150,000 is only for the inhabitable space on Earth. We're not talking about deserts because we know we have to work with the people to invest in their stations because it's a citizen science project. And these people invest their time and money to create such a station, and we develop all the things around the hardware, the software that goes into a do-it-yourself equipment that someone can create the station. The number 150,000 is due to a certain distance that we want to see those stations, let's say, in average apart, so that triangulation makes sense. Especially in the next image, you can see that. With our benchmark that we set is to detect and recognize and track the ISS. If we can do that, then everything, let's say, more or less moves in our air is trackable and recognizable with our system. So that's why we use the ISS as a benchmark. And that's just a short idea about triangulation. We have, of course, several equipment inside the station. We have optical equipment, we have RF equipment, and those have different ranges. And yes, that had to be considered as well. We're not there yet. We start with the optical part right now, and our idea is to go deep into the RF thing next year in 2023. That's more or less like a station looks like. I have to say it's a 2-month-old picture. It's not totally different now, but some parts are totally different. But that's the idea to give you. This is a station that is made from ABS thermoform plastics, and our stationeers can purchase them and put all the electronics inside, so they have a secure platform that they can grow on and we can develop on. That's a quick rundown on our schematics. We have several boards, of course, and several sensors. And our software is, this is an old image of our schematic, but it's, now we're going into more robotic system where with sensory systems and, let's say, higher level neural networks or control programs that take, like a robotic system actually does, kind of. Yeah, these are our teams. We're now running with 8 teams and several people doing hardware and software. And this is just a screenshot of our software that it's in development right now, so we cannot give you demo at the moment, but that's just a UI design of how it should look like. So things have to be placed in such a map so that we see where the station is and what object is moving where. And with all this recognition part in it, whether it might be a plane with some liability, or it might be a drone or a bird, and this is also a big part in our endeavor, is the UAP topic, where things are seen by so many people in the sky which do not resemble normal things like planes, birds, drones, but might be optical illusions, might be kind of air phenomena, atmospheric phenomena, could be all kind of light reflections, could be man-made structures. But there are some still left that are rather unknown and behave rather strange. And so that's a topic, the UAP research, that drives us, let's say, very much. And that's why I actually here to create data that can be used scientifically to analyze what these phenomena might be, whether they can be explained in a traditional way, or we have to reconsider our physics, kind of. So, coming back to Crane, stop sharing, right? So I hope you got an idea and you're not frightened now that we are talking also about UAP research, right?
Yes,
You still might flee away
amazing. Oh, no. I'm very happy with what I saw, because everything looks really amazing, and the fact that you're so far ahead and you actually have hardware and a software platform, that's really impressive. Like, wow.
Thank you.
Yeah, we are still considering us in the development phase. We started last year, end of last year, and yeah, we're now trying to create more or less real parts and real software parts that work together and so forth. So it all goes by many pieces. And I hope that we reach the point very soon to create a picture of all those mosaics. But yes, we are right more or less at that point in time in development. And because we are there at the point where we're not having a final software or a final decision on hardware, and we're still in an R&D phase, that's why we have so many questions. And that's why we are happy to have you here. And maybe I might kick it off with the first question. All right, so
Sure.
I'm switching back and forth because I do not have all the questions in my head. Okay, as far as you know right now what we're doing, and we have to deal with very small and fast moving objects in a very noisy background that changes rather quickly. What method of detection of such small and quick moving noisy background detection method would you consider is best fitting for our purpose?
Okay, so it's a very good first question. I would say methods directly might be like there's a ton of methods that exist. The first thing I would ask is like, what kind of family of methods would you first search for? And there's really different methods that would be applicable to this particular case. All of them are essentially based on anomaly detection. You try to look for patterns, or patterns, whether temporal patterns or just visual patterns, that are unlike everything else that has been observed or recorded in the recent past. And any kind of modeling method that will try to do that should be able to solve this problem. So in terms of the family of methods, there's ones that are really just based on machine learning and neural networks. There's ones that are based on background subtraction, like I did many, many years ago. I think what people are most interested in today in terms of the literature, it's going to be neural networks, because those are everywhere. But are they the most relevant solution here? Maybe not. So regarding this particular question, you say detection of small, fast object in noisy backgrounds. The first things I would actually ask to go and dig a little deeper is, what is small, what is fast, and what is a noisy background? All of those things depend essentially on resolution. So what kind of resolutions are you typically looking at for this application?
Christian, you want to contribute here?
To point out, noisy backgrounds means something like signal-to-noise ratio about 1 sigma. This would be considered as a bad condition. And if the signal-to-noise ratio is about, let's say, 3 to 5 sigma, then you have very good conditions. A fast object, the sky rotates within 1 day 1 time. So every object that is faster than that can be covered with a normal telescope. For the part that we're using at the moment, it's the old SkyCam. It's just let's say a Cyclops with a fisheye camera and a very high resolution camera. We can track objects up to 15 to 20 degrees per second. This can be traced, and a telescope can be slewed at that pace too. So everything else, let's say with a frame rate that one frame takes it is 20 frames per second. This is our goal to reach. So if we can say if an object moves 1 pixel to the side within 1 frames during those 20 frames, this would be considered, let's say, doable. For every other thing, we have to I think subsample it. This is for the speed. So 20 frames per second is the limit that the camera can do. What else?
Resolution?
Yes, the resolution that we are facing now with the camera is meant to be 3600 by 3600 at 20 frames per second and a final image dynamic range of 16-bit. This would consider of having a very, very huge amount of data transfer rate.
Yes,
and
correct. Oh, that is.
We have to deal with that.
Impressive.
And we are trying to use since these are cameras that are normally used for astronomical imagery, we try to use astronomical data reduction, like first producing a master bias, subtracting it from all the other data, like the dark current, like the flat field, and from the actual data frames. So we have basically a good solution for background subtraction because it's done by during the data reduction process. And therefore, we can maintain with a good calculation of the exposure times for the images to reach a certain flat curve for the signal-to-noise ratio. It only will change during dawn and during sunrise and sunset. And therefore, we have to find a solution that this is all done very, very quickly so that we can say, okay, let's say an object that is rushing over the sky with, let's say, 40 degrees per second can be tracked. Yeah, I think this is what we have to achieve.
Yeah, it gives very good ideas already, like those numbers. And specifically regarding, let's say, the size of the objects, are you looking to track any size from 1 pixel up, or are you looking for sizes in particular?
Since we have the problem that there are no cameras around with, let's say, 144 megapixels using a pixel size of 1 micrometer, the actual setup that we could get to work at the moment is this fisheye lens with 60 millimeters in diameter, so the resolution is around 1.6 arc seconds. and a camera that fits with the Nyquist-Chenin criteria for the sampling theorem, with 2.3 to 2.4 micrometers for the pixel size. So 1 pixel will be ISS. And because it's bright and it's moving and our atmosphere is full of gas, which is nice because without we couldn't breathe, we've got seeing, and this smears the object, let's say like the ISS a little bit, and so we will be about 4 to 5 pixels as a detection possibility. Yeah.
Okay, so it's very tiny. Okay, so
Yeah.
to give a
But
little
okay, let's say 747 will be I think around 50 to 70 pixel.
Yeah.
10 and 15 at a distance of 50 kilometers. So yes, we calculated what we will need as optic and camera resolution. So just to be on the safe side.
Okay, that's good. So the smallest that would be practically trackable and identifiable would be the ISS at a few pixels, and a typical like actual airplane or something like that at a high altitude would be in the tens of pixels typically.
Mm-hmm.
Yes.
Okay, that's very interesting. So,
and since we know where the path of the and the ephemerides of the ISS, it's a good benchmark for us because it's a reoccurring event, and we can say, okay, if we can track it, if we can recognize it, it has a certain path, then we can make sure that we detected the ISS, even if it's just 1 pixel. And it's 110 meters long in diameter with an altitude of 422 kilometers with a speed of 7,700 kilometers per hour. So we have a very, very defined setup for that, so we can track it.
That's good.
Okay.
So in terms of the models that would typically, like, that could be used to detect such objects, I'd say a background subtraction approach will work with any kind of object size because it just works by, as you know, it's background subtraction. We just create a model of what the background should be without anomalies, and then the anomalies can have any shape. Typical neural networks, the ones that you would take off the shelf and just say, I want to train on, it's like airplanes. Most of them do not work very well at resolutions of objects that are just a few pixels. Mm-hmm. They just fail. They're not really designed for that, unfortunately. In this case, in the tens of pixels, you could use one of those models off the shelf. It could be interesting in terms of adapting one of those models to a particular use case here, so that's possible. But otherwise, background subtraction approaches might be an interesting, at least pre-processing stage to do actual classification. The next question I was asked is related to, let's say, just detection, classification, tracking, the different approaches, the different models. So personally, I've worked a lot with those in the past. I still work with those today in current projects, but it's mostly with neural networks, just because that's the flavor of the day, and for practical industrial applications, that's what everybody's using. The thing is, detection works very well with neural networks, but again, it's that limitation of when the objects get too small, or when we do not know the nature of those objects themselves. Like when we truly want to treat them as anomalies, and they could be anything, and they don't necessarily have a visual pattern to them that allows us to classify them as like, oh, okay, that's a kind of airplane, then those fail. Classification and detection can be tied in a way just because that's how they work. But for typical models, the way they work when we're talking about tracking or localizing an object, that's part of a regression objective where we just try to regress the XY position of an object in an image. And in a way, that's not super interesting, I think, in this case, because everything you do, you could summarize it as we want to detect and we want to segment in terms of pixel, like create a mask of pixels that says this is the object and everything else is not. So, and typically those approaches, they're not based on object tracking or object localization approaches, especially with neural networks, they're more accurate if we work at the pixel level. So that's already something that's interesting. So in terms of the next question was regarding the types of neural networks that can be used for object detection, classification, tracking, all those things. Convolutional neural networks are definitely the one that is the most commonly used in practice. They've been around for 20 something years. They've been very, very efficient and useful for more than 10 years now. We use them extensively across so many applications, including remote sensing with imagery that could be somewhat alike yours, and they work very well. Other types of neural network, there's definitely several out there. I think most of them would not necessarily be very interesting or useful at this stage. If you want to process sequences of images, it might be interesting eventually to consider recurrent neural networks or 3D CNNs or things like that. But at this point, I would say if you do image processing with one image at a time and try to analyze the content, that would probably be a very good first start. I don't know if you had questions about any of those models or neural networks in general before I switch to hardware.
May I put a question here? We are working with a resolution of 3600 by 3600, and there's just a lot of noise and very few signal. And we already knew that using neural networks from the shelf would not apply just to that resolution. They would go for, let's say, 600 by 600 pixels, and if we downsize them, then the 1 pixel goes away. So
yes, and this is something that is extremely interesting in the context of typical applications of neural networks in remote sensing. So they have the kind of the same problem as you, a full swathe of like, hey, we just scanned the entirety of North America with a satellite and gives us images that are thousands of kilometers long. How do we actually process that with a neural network? The way they do it, they cut them into tiles and they process the tiles. And doing so is not as efficient as if we process the whole image at once. We might not have access to as much context when we're trying to do the interpretation within the image. But in practice, having a 600 by 600 tile within an image that's way bigger is still enough context to do whatever we want. So in this case, I think this same kind of practical solution would be applicable here, no problem.
So it's segmentation and parallelization to speed up the whole process, as we thought it would be. Yes.
Can I ask a question?
Yeah, Bojan, go ahead.
Okay, let's say these objects, moving objects, UAP, UFO, they are using anti-gravity in order to move. Maybe, right?
Yeah.
And how can we dealing with such a things? Because these objects flickering, not just because air, just because anti-gravity, maybe. Just saying, how can we be sure maybe this is just a projection, what we see, not really what really are? I hope you understand what I'm trying to say.
I think so. So in a way, we will still be limited by what the captor or the sensor can see. If the sensor is really built for visible spectrum imagery and all that stuff, we will only be able to see variation and patterns within that very tight spectrum. So whatever happens, whatever type of object you're trying to track, you just have to make the assumption that those patterns will be visible, or you have to use a wider spectrum or another sensor.
Yeah, of course. But do I understand you right? Your approach would be you were proposing to take this stream of images that come from the camera and cut it into slices and let neural networks work on those local slices. That's okay. And you would suggest to go with a neural network only without the classic motion detection?
Then that is a very, very good question. So if we talk about the pipeline, okay, the first huge limitation of neural networks is that they require a lot of training data to be able to recognize objects and detect them properly and recognize them later in real images, they need to be shown those objects often and often and often. So that's kind of a failure point for the whole anomaly detection pipeline, where we're looking for objects that we don't know what they're going to look like. So there definitely are ways to train neural networks to try to detect anomalies without foreseeing what the anomalies are going to look like, but this is somewhat difficult. But it brings us back to the whole point of neural networks need training data. So if you were able, for example, to generate training data by just having these videos and like tons of frames of the sky with no objects, and then artificially add objects at random positions. But if you yourself are adding them with just programmatically, and you're blending them a little bit, but you are placing them wherever you want, you can keep track of that and then feed that to the network to train it. You just then give it the image and say, hey, guess where the object is? And that's something that's done a lot in practice, but the realism will never be as good as when you have truly like true objects that you see in images and then you annotate manually and then you use that to train your network. So there's definitely many ways to do that, but all of them are essentially shortcomings. The advantage of using a background subtraction approach is that it does not require any training data. Essentially, it's a very dumb and small model that just does differentiation between what I've seen in the past and what I'm just seeing now. And that can be a very interesting and good pre-processing stage to actually feed, like decide what data you want to feed into a second stage that is a little bit more intelligent, that maybe a little bit harder to train because you have less training data, but in a way, the combination of the two would still be very practical and interesting here.
So, if I may just talk for all of us, what we do now have is a tracker, but Mike, maybe you can add that more. We have a tracker that recognizes objects based on background subtraction and edge detection, I'd say. And then we know where. Yeah, sorry, Mike. I'll just give you a short rundown of the pipeline that we use right now, and maybe then you can jump in and go more in detail about the detection part. So
do you want me? Okay.
Yeah, sorry.
No, you crack on, mate. Sorry. I'm interfering.
No problem. I call you in 10 seconds. So the pipeline as we have it right now is on the tracker, only on the tracker, is that we use more or less classic computer visions, background subtraction, as you already mentioned. And they're making some blobbings, and then we know where it is, and then we can follow that, let's say, from frame to frame. But when we follow that from frame to frame, we also get, let's say, cropped images from that part. So we crop the event by, let's say, 64 by 64 pixels, as it is right now. And then we have a very tiny image where all these images are of the same size, which very easily can be fed into a neural network training stuff. And because when we track something, there is something in this track normally. But still, our tracker tracks things that are not there. Yeah. But now, Mike,
okay, this is already it's a good pipeline. And the fact that you're cropping and you have these very normalized, let's say, sub images, 64 by 64, something like that, it means you can actually accumulate a fairly large data set fairly quickly of examples of, hey, this was strange. I saw this. I'm not sure what it is. I want to analyze it further. This is very cool because if there are some neural networks that can be trained to do anomaly detection using a data set that the only training data that we have with the data set is, for example, if you have 10,000 images that are 64 by 64, but you know within all 10,000 of those, there's nothing interesting. You can train a model to recognize what this distribution of not interesting is. And then with something, just you give it an example and you say, is this within the distribution that you saw in the past of not interesting? If it thinks it's outside it, then it can classify, nope, it's not. And then you can flag and say like, okay, I want to send this to a human for them to actually look at. This is something that's very doable. And in practice, there's a lot of off-the-shelf models that exist that can do that very easily.
So neural networks is more human-like than AI.
Yes, absolutely.
AI is
Yeah.
basically machine. Yeah.
Yeah, the term AI, for example, I work in a research institute where what we do is AI, and it's in the name of the research institute itself, but internally we hate using AI because it's a buzzword, it's used for marketing, it's really horrible. So what we
Yeah.
say often, we say machine learning, and machine learning, what we mean by that is we teach a model, or we teach just, it's like a black box. We send in some data, we send in a signal, and then we punish it and encourage it to give it the same response that a human would. And that's essentially all we do. So everything that is machine learning, everything that is AI these days works essentially based on that. It's we train them to do the same thing that humans would, and some of the time it actually works. So that's what we do.
I think it's it's about the definition of AI, and because it's commercially used in let's say faulty way, this produces problems. And we already discussed those internally, and yeah, we're on the same page here, of course. Yeah. You said the idea you brought up just now is very interesting, that yes, training a neural network to detect nothing is just, let's say, an altered version. So you can subtract the nothingness from the real data that you have. And yeah, I think this can speed up the whole process to say, okay, these subsamples contain nothing, so I can avoid them and concentrate on the bounding boxes with actually having content. And it's to opt out the nothingness. Yes, it's a very good idea, and I think
I'll definitely send you links about this afterwards. And in terms of the literature, people that work on anomaly detection with neural networks, they separate this problem into the problem of known knowns, known unknowns, unknown knowns, and unknown unknowns. And it's very confusing. And I remember Donald Rumsfeld trying to explain it to journalists during the Iraq War or something like that. And it was insane because it's very complicated, but it actually makes sense. Do you know the objects that the model will not see? Do you not know the objects that it will see? And things like that. So in our case, we have to identify, okay, the data that we will have at first to train our model, what kind of data is it? Do we have examples of what we will see in the future? No, not really. Because if we're looking for any objects, then we might have a few examples of actual anomalies, like, hey, this was a weird jet that we don't know where it came from, and we have one or two examples of this thing and stuff like that, but we won't really have many of those. So I are already identifying which regime we're going to be working in, and then identifying which approaches are compatible with it. That's a huge first step.
So I have a small question. This is Ido. So you spoke about like having like a human intervention. So it's like a kind of supervised way to teach the machine learning. I was thinking more towards, is it possible to do an unsupervised model? Because in the end, like we spin around, space, and even flights, even stars, they're all repetitive, around like 24 hours, maybe a few days window, right? And,
yeah, there's a lot of them.
Yeah. So my question is like, is there a way to have the neural network kind of learn the patterns over a long period of time of, like, let's say, a week, right?
Yes. This is a very interesting and active research topic in the literature. I have a lot of colleagues that are working specifically on that. It's called either active learning or continuous learning.
Yes.
So yes, it would be super, super useful and really ideal in this case, but it is very difficult to do it in practice just because it's hard to actually get a recipe essentially to train one of those models that behaves well over long periods of time.
Yeah, but that's something I can probably do, like not on the station, but on the cloud to improve the model, right?
Yes, absolutely. And it's something we can definitely consider. Let's say if we train a first generational model and we apply it in practice, it gives us a few like flags, and most of them are bad. Then we annotate the bad ones, we filter them out, we give them back in the cloud to train a second generational model, and we keep this
Yeah.
loop going just to improve the model. And yes, it's something that's done a lot in practice. The thing is, it's still very manual in a way. The best would be to automate that whole process, and I think that's
Yes.
what a lot of researchers are focusing on. But if we can do it manually, then still very, very useful and practical.
So putting up a training net that uses self-orientating maps would be an approach.
Yeah.
I'm not super familiar
That's what I
with
was thinking, Christian.
Self-orientating?
Self-orientating maps is a type of neural networks that uses unsupervised learning to come to produce the patterns that a neural network, let's say like multi-layer perceptrons, later uses for the object detection. So because of the self-orientating nature of a map, because the pattern is a map, you can let it run on its own and find the pattern that you're looking for by itself. So this might be a help with that.
Yeah, so
that
I
could
was
be
thinking.
interesting.
Yeah, so Christian, I was thinking about that, and then back to what you said earlier, that we can inject some objects into like a map. So I'm thinking about it as a simulation. If I can create this rotating map model in a simulation, and then put unknown objects on it, I can probably create an unsupervised model that teach itself.
How often?
Like a game in a way.
How often?
Hold on, Boyan.
How often neural networks need to be supervised by humans?
That's a good question. So typically for most, let's say, industrial applications, we train them once. We look at the quality. If we have a testing set or something to just evaluate them, we see, okay, is it within like the norms? Do we accept this? And then that's it. We're done. It's never trained again. It's possible that if the data itself changes over time, like for example, if we're in a factory setting where for some reason somebody changes a neon, and then the color and the lighting is different, and then there's a camera on a treadmill that looks at the image and it's different, then the results might get worse. And sometimes that's a flag that's raised. We have to retrain the model. But typically, if we process the data that always looks the same and the distribution of the data does not change, then we can keep the same model.
Or if we use augmentations to modify the training dataset to simulate like different lighting conditions.
Yes, that is hugely useful. I would say typically it's always part of the recipe. We always want to use augmentation as much as possible because it just provides us with more data, more varied data.
Yeah, so this thing about synthetic dataset, there is one dataset called ShapeNet. It contains a lot of, for example, 3D models of airplanes. So maybe we can capture a lot of data from our fisheye, and then take a 3D model and calculate where it sits on a curvature of the lens, and take a screenshot from this angle and then apply it on top of the frame.
That would be amazing because it would give you, as you say, a large collection of 3D shapes that you can work with, and the diversity in those shapes would help the algorithm understand a lot that, hey, okay, what you're going to be looking for is very diverse, all that stuff. So that's a good approach, but there is one caveat. It's the fact that when you create the pipeline to add the shape within the image and you just embed that shape, that pipeline is likely going to produce artifacts within the image. Sometimes it's just a blending, it's not going to be perfect. Sometimes just as a human, we're like, okay, I'm just going to blend a little bit more to like add a layer of like almost Vaseline over the lens or something. The algorithm will detect that. And it is like neural networks love cheating. And whenever they see those artifacts, they will go like, okay, there's something here. I know because I see the artifact. But it didn't truly find the object. It just found the artifact.
Yeah, I heard of a case when neural network learned the noise pattern from the camera because dataset was captured using 2 cameras, and they figured out, okay, class A has this noise, class B has this another noise.
And this happens a lot in practice, unfortunately. And especially with very difficult tasks, like if we're trying to detect or localize or classify something that is very rare or very difficult to find, then we're gonna have to be real careful with that. Yeah.
So if we would add a layer to the neural network that with a calculation of the artifacts that the optic will produce, like torsion, like reflexes, like anything else, this would help the neural network to opt out all the things that it shouldn't learn. Let's say, okay, the fisheye lens has projections, and it depends on the optic geometry, which projection is used to generate an image, and this has to be calculated for the simulated objects too, so that we get the right shape that should be detected, and not run into
like, because
the easy learning path for the neural network. So it detects, oh, this is an object I already know. Yeah. So we have to modify the simulated training data in order to not get faulty detections.
To apply distortions to airplane if it's on the edge of the lens. Is this what you mean?
That would be at a height of 30 degrees above the horizon.
Yeah.
But anyhow, wouldn't it be the way that if we create such material from, let's say, 3D objects that we put in a landscape virtually and on all distances and forms and shapes, but would that not imply that we train the neural network exactly to those shapes? And
yeah, it would.
We can only use those 19 shapes we know, let's say several birds, several drones, on the knowns.
We can have an algorithm that alters those shapes concerning how many pixels the projection already has in the end.
I think this is actually a harder approach than doing unsupervised clustering on real data that we have.
I mean, we have data. Pierre-Luc, just to give you an idea, we have data. Yeah, we have tons of data. We have terabytes of data. It's video material, and what we do is we process this material, because for development it's more easy to, instead of doing it with a camera, because in these videos we know what it is. Either it's a video where there is a bird, or hundreds of birds, or planes, or several planes. Because we can watch them, of course, and that's from these we create these crop pics from. But if we create this training material, I'm really concerned here. Yes, of course we can.
Yeah, it's not real deal.
Yeah.
For example, I use this method to generate a lot of cars from different angles, like from the front, from the back, left side, right side, front, left. And it was a car in a full frame, and it was still not nowhere near to the real data set that we can capture from the nature, because this method only reached with synthetic data 85% of accuracy in classification, but when we bought a real data set, it went above 95 for the because it looks like a video game. It's not nowhere near the real life.
Mike, you have a question?
Yeah, I was just wondering if I could, I was going to see if I can maybe draw the conversation a little bit back towards background subtraction, possibly.
Thank you.
If you guys are, if there's maybe some time to discuss that. So I'd like to kind of get your view on background subtraction, and also its usages in our, like, with what we are trying to achieve. If in your opinion there is a benefit exploring it further. So one of the things, so I'm just going to give you a little bit of context, and then hopefully, so one of the things is we use. So I've written, well, not me alone, but with another guy, we've put together a little application that effectively tries to track an object going across the sky. A big part of that is using background subtraction. We use OpenCV quite a bit. We've also stumbled across another library called the BGS library, and that's actually how we found your details, because you were contributed to a couple of the algorithms in that library. I was just hoping to get a bit more of your experience, like just a view on your opinion on background subtraction. Do you think it's relevant
Sure.
still?
And CUDA.
And then maybe if we can explore maybe some hardware options and just talk about, just that sort of
Sure
stuff in
thing.
general. If would that be okay?
Yes, definitely. So for background subtraction in general, it was a topic of my master's degree and part of my PhD. Those methods were generally very popular back, let's say, between 2000 and 2015, and they kind of slipped out of the spotlight in recent years just because machine learning and neural networks have been so popular. But they are still being used a lot for video surveillance, for low energy applications, embedded device, edge devices, all that stuff. And in this case, yes, I do believe it could still be very, very useful, especially in terms of pre-processing your very large scale and high frame rate images into sections or tiles or smaller images that can be interpreted using a second model afterwards. So in terms of actually implementing a background, like a modern background subtraction method, there's definitely a lot of the old methods that could be revisited, where we just change some of the features, like the image features that they use, to use more modern ones, and they will perform superbly. They should still be very good because the approach, the algorithm itself is very simple, and most of them are very easy to adapt and just bring back to modern times. One of the big disadvantages of them, like for several of them at least, was the fact that they were only ever implemented on CPU, because most of the people that were interested in them were either academics or vendors that were working on edge or very embedded devices that knew, hey, we're gonna have our own processor, so don't worry about CUDA, we're gonna do our own. So it's essentially where things were left off with the literature. Personally, I implemented one method like that in the past on CUDA, and it worked okay. But it was more of a, I want to see what it would take to actually do it, and it was fine. I think those methods are very good candidates for processing images on GPUs, just because they are so lightweight that you could do the 3600 by 3600 image at 20 FPS super easily, and then take the results, like the masks that say there might be something here, something there, and give that to the next model. So yes, that would be very good. And in terms of actual, let's say, devices or hardware that would be able to do it, if we stick to stuff that we know, like CUDA itself, a Jetson, or any of the NVIDIA Jetson boards, like the TX boards or the Jetson Nano, or any of those, would be super easy to use, because you just take the algorithm that runs with CUDA off the shelf, you plug it into the feed of the camera through that board, and boom, you're done. It gives you masks, and it costs $50. So that's something that's very easy to do and doable.
So yes, you were talking about hardware right now. Yes, the Jetson boards are considered here since, I think, 2 years right now. We are now reconsidering this board because, first of all, those boards are very hard to procure at the moment. And if you buy one, normally you would buy it's $100. When I bought it 2 years ago, I bought several, but today you almost buy $1,000 for one board. It's ridiculous.
Ouch.
So we were trying to rethink this and go, and this also is a split point where we do not know where to go, because if we have to stick to CUDA, then the path is obvious, of course. We have to go with NVIDIA graphics, whatever, boards or add-ons. But is there another way? Is there another better way
There
to
definitely
do?
are. Well, to replace CUDA itself, you can use compute shaders directly through any like graphics libraries like OpenGL or whatever, and most of the embedded chips will have a graphics library, and compute shaders are probably enabled in that. So whatever happens, whatever chip you have, if there's a GPU, you're probably good, but it involves a lot more just work yourself in terms of engineering. Otherwise, I know Intel has been working a lot on embedded chips, and what was the name of the competitor to CUDA a few years ago? I don't remember the name.
A
It's
competitor
been
to
so long.
CUDA.
The
Yeah, it was.
AMD cards, I think, were FireGL.
Yeah, the DNA
Yeah, but
or DNA
but
3,
they,
AMD,
yeah, but
I think.
they just got around 35 to
It's
40% of what CUDA could do, and
yes,
they were nice for rendering parts, but not for neural network and image or pattern recognitions.
yes. So in terms of let's say neural network performance and everything, NVIDIA is still the number one, just because NVIDIA invested a lot of money and a lot of effort several years ago into making sure that they would have the market to themselves, and they still do. It's unfortunate, but it is what it is. These days, I think Intel is working a lot with a few toolkits like OpenVINO and those things to actually offer better solutions for embedded neural network processing on many platforms. So OpenVINO is not great, but the platform I was thinking about in terms of an alternative to CUDA that was open source and everything, it's OpenCL for Open
CL.
Computing Language. I personally never implemented anything in it, but back when I decided, hey, I'm going to run my thing on CUDA, that was the alternative. I haven't heard of it in recent years. It's still being like updated with stable releases and all that stuff. It's a cross-platform language, so it's for ARM, it's for GPUs, it's for all kinds of stuff. But again, if you want to implement an algorithm in OpenCL, you will have to do a bit of engineering, and there's a lot of effort into understanding the documentation and understanding the API and all that stuff.
So from your perspective, which way we need to go, hardware speaking?
Did you
So in
understand the
terms of
question? Yeah.
hardware, if CUDA and let's say Jetson boards and all that stuff are really, really an issue, that's unfortunate. It's really unfortunate because it would be the simplest solution by far. Just
True.
getting Jetson Nanos.
Can we use like a PC?
Bojan, we cannot hear you good enough. Please speak louder or put your microphone on.
Can we use like a computer boards, motherboards with video card?
Of course.
A
Can
micro ATX computer would be interesting. It wouldn't necessarily provide a lot more computing power. Typically, what's really needed for image processing or anything like that is a CPU that can do a lot of parallel processing. So that's why GPUs are very, very nice and all that stuff. Jetsons, they have a few tensor cores and all that stuff, so that's very nice. Raspberry Pis, I'm not really sure they have any kind of parallel processing power at all.
No,
So
micro
again,
ATX with NVIDIA GPU, like RTX 60. They also have tensor cores and they are accessible.
In that case, I would say any kind of GPU, an actual dedicated device that can be used would be good, no matter which one. It's best if it's easy to use in terms of APIs and all that stuff, but yeah, anyone would work.
Speaking about availability, the motherboard, micro ATX or whatever is available for everybody. Jetson Nano, Jetson whatever is stuck.
Yeah.
People, it's so high,
Yeah.
and
Okay.
we can be stuck with that.
May I go back to the question from Mike? Basically, actually, hey, there you are, Mike. Yes, we do know we have issues with hardware, and that's not easily be solved. And I think the market has to help somehow here. But may I go back to a software question, and basically the question of Mike. So background subtraction is a yes from your point of view. And if we can make
Yes.
a background subtraction method be used with CUDA and CUDA cores, that would be the way to go. Is that what you say?
Yes, if I was building a solution from scratch, it's probably the way I would go.
Yeah.
Background subtraction first to highlight regions of interest that, hey, maybe there's at least movement. We detect movement, so let's process these, and all the other ones we just dump them. We don't need them. And then second stage would be some kind of neural network to do higher level processing. Like, let's look at the content now and actually try to classify it in terms of, I know this, it's not interesting, versus, I don't know this, it might be interesting.
Okay.
Would it be a nice idea to put the background subtraction as part of the reduction process, because it would speed up both? Because we already have to do signal reduction to get an analyzable image. So if we would speed up the process by combining that and giving and putting out the subsample images right away, so this could. The problem we faced earlier was that the Jetson Nano is not capable of providing an image stream or the images itself, because the cameras, the buffer is too low, and we have too much data from the cameras coming. So we decided to go by a Pi 4 for applying the camera and the data, and then using ROS2 to provide the data to the Jetson Nano, and using Jetson Nano as just the GPU part. This was the plan that we are
it's an interesting plan,
use.
and if you already considered using two boards with communication between the two boards, then it does open the door to a few more steps that could be very interesting. So the first step is, if you do acquisition on a Raspberry Pi, because it has the buffer for it and the memory and all that stuff, that's good. I personally think you would be able to run a fairly modern background subtraction algorithm on a Raspberry Pi, maybe not at a full 20 FPS, but at a reduced frame rate, get decent results, and ship that to the Jetson, and it would be possible to run both like simultaneously. It's actually
this
very nice
was
because,
the idea of doing so.
Yeah, I think that sounds like a good idea, because otherwise we would have to switch back and forth between using CUDA cores for background subtraction versus neural networks, and neural networks typically they definitely are slower. Even quantified and quantized ones, they will run slower. They're just big.
So if we split it up like this, that we use the background subtraction in a very early stage and reduce the data and manipulate it like this, so that we can use the hardware advantage for the background subtraction, let's say as part of the reduction process, then we could tear it apart and make room for the neural network detection on the Nano, so we do not have to skip all the Nanos that we already bought. And those, because we try to be a little backward compliant to those who bought SkyHub stuff, and we want to we want to, not that the people are angry about us that we moved further with the hardware. So reusing it would be nice. And therefore, we have Jetson Nanos already, and maybe some HG exports and like that. So the idea could be that we put the background subtraction part into the reduction segment and speed up the whole process with that.
Yeah, just to give you a short context here, Pierre-Luc, Christian was referring to hardware that we stick on since more or less 2 years. And people already purchase those hardware, and we always had this feeling we have to still to support it, but what to do if we have to change. So that's what he's referring to. Mike, you wanted to say something? Mike? Or
No. I just all I wanted to say is that we might just need to give Pierre-Luc a bit of context to that to what Christian said, which you have done. So that's exactly
Thank you. Same mind.
That works. And also regarding the use of a Raspberry Pi, I know Raspberry Pi is their ARM processors. They do have a lot of SIMD special instructions that can be used to speed up things. For a background subtraction library, a lot of them, if we implement the algorithms right, we can actually make good use of those instructions and speed up processing by a huge factor. It can make a huge difference. I've done it once in the past on a microprocessor that was for surveillance purposes, and it made like a 10 times speed up improvement. So it might be doable. This is something that would need to be benchmarked just to see like how fast is it actually going to run and which algorithm, because there's a lot of them.
Could you, because there are a lot of them, could you give us just a feeling of where to look for, what to look for?
Yes, in terms of the algorithms, the classic ones, the one that is the most lightweight yet fairly interestingly good and robust, Vibe. The Vibe algorithm. It was published by a professor in Belgium. It is patented, unfortunately. I'm not a patent expert or anything. I've been told in the past that it would be so easy to just bypass the patent, stuff like that, blah, 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 if you want to use it in commercial purposes or anything like that. I don't even know if commercial applications were here.
No.
No? Okay. No. Then you can use it as is, and that's wonderful.
Okay.
My own algorithms, the one I've developed, they were essentially improvements over Vibe. But as soon as you improve over that very basic algorithm, it starts slowing down significantly. Because Vibe, the way it works, it's just... how can I explain? For each pixel, you create a pixel-level background model, and it's randomly updated. And then whenever you do decisions, you make decisions to say, okay, is this background or foreground? Then those decisions affect how often you update the background itself, the background model itself. So the algorithm, it can be literally implemented in like 30 lines of code. It is the fastest I've ever seen one of those background subtraction algorithms run. Or we're talking thousands of frames per second on a GPU, or a very decent, probably real frame rate on just CPUs.
And you think that would work on a Pi too?
Probably yes. I've run my own algorithm in the past on a Raspberry Pi. I don't remember which model it was. It was maybe like 6 or 7 years ago, so it must have been one of the older versions. Mm-hmm. And mine ran at 30 FPS on a Raspberry Pi board for images that were, let's say.
Nicola, what did you say?
Yeah, the resolution.
Resolution.
Yeah, in my case, I was running, I think, VGA resolution, so 640, 480 at 30 FPS for an algorithm that might have been 10 or 15 times slower than original Vibe. So if we scale everything back up, you might be able to do, 10 FPS on the 3600 by 3600 image. But I'm being very optimistic here. It's probably going to be maybe 1 FPS on that big image. But still, 1 FPS on that big image, you'll be able to get segmentation masks. They're actually useful for all 20 frames, even though you see only one at a time.
And you have to take into account that it must be a Pi 1 or 2, and the Pi 4 at the moment runs with at least 4 cores with 2 gigahertz. So you've got a speed up in hardware too. So we might reach those 15 to 20 frames per second.
Okay, interesting. Yeah, Mike, I think this task goes to you, right? To test this on the Pi, right?
Oh, yeah. Well, all I can say is so I'll give it a go. I have challenges with regards to getting the kind of frames per second that you guys are referring to using, some of the background subtraction algorithms out there. The one that I'm kind of been using currently is the weighted moving variance, and that seems to, from a detection point of view, work pretty well out of the BGS library. So I'm not a CUDA guy, so I don't know how difficult it would be to implement that algorithm into so that it would use a GPU. But I can try it on a Pi and and see where it goes. I mean that's all we can do, right? And we can just do it so that I'm just trying to think. Yeah, so it's something. It's an action for me to take away that I can explore and then kind of give you guys a demo of it, really, and see what you guys think. I mean, I unfortunately don't have the skill set of to basically disassemble that algorithm and write it in such a way that it is incredibly speedy on a specific hardware device. So I don't have that. So all I can use is what is currently available, basically. But I can definitely do it. Yeah.
Yeah, and as far as we heard today, most of these BGS libraries are not GPU based, so the Pi has no GPU, so
yeah,
it is CPU anyways. And you were saying you were using. Can you repeat this word? What kind of BGS you're using?
Single instruction, multiple data.
Oh yeah, SIMD instruction. Yeah, SIMD is the acronym to mean exactly. It's single instruction, multiple data. Essentially, it's instructions that instead of just taking one value in memory and processing it, like applying an operation on it, it can do that with multiple values in memory at the same time. So since typical background subtraction methods just apply across lots of pixels at the same time, then it's clear that, hey, okay, running a bunch of pixels with one instruction would be amazing.
Okay. Hey guys, it's we have 1 hour. We are over the 1 hour. If there are no more questions, then I would say we wrap it up. Are there any more questions? Okay.
For me, still question is hardware.
Yeah.
It's a big question.
Pierre-Luc, thank you very much for having you today. There were just some questions. I told you we have hundreds of them, but these are the most important ones right now.
I would say if you want to do any other meeting like this, I'm totally willing. This is really good. If you have any questions that you want to send through email, also I'll answer absolutely. It's great experience.
You are now on Discord and you have a tag Duck. You will stay on Discord, or you will remove your account?
Thing.
You will? You will stay?
Yeah. I use Discord for lots of things in general, so sure, I'll stick around and works.
Thank you very much. That's great. So yes, whenever we have a new milestone, we will try to come back and with questions, something like that.
Also, just so we are here every Sunday, around about this time. So if you ever want to drop in, please feel free. You're more than welcome, and it'll only be a pleasure. So yeah, I just wanted to give you an invite, like an official invite, please. Good. Yeah, it'd be great if you could drop in occasionally and come and have a chat with us. That'd be awesome.
Okay,
sounds good.
You're heartily welcome every Sunday, but I know it's Sunday and you have family, so okay, this was a kind offer. Thank you. Okay, so
right, well,
Pierre-Luc, thank you very much for having you. And when we have questions, we might drop at your place. Right? Perfect.
Sounds good.
Thank you very much.
See you.
Thanks
have a nice Sunday.
Yeah, thank you.
Thank you very much. Thank you.
Thank you.
So I'm still on record. Shall I go on with recording and we have a little discussion? Let's say a feedback loop right now about what we learned. I think it's good.
Yeah.
Let's do that.
Yeah.
Mike,
Yeah, sure.
why not shoot off? What have you learned today?
Sorry, who?
You.
Oh, me.
Mike.
Oh, sorry. Yeah. So, I like the optimistic view. That's so my view's been quite pessimistic in a way to try and achieve the frame rates and that sort of stuff. So, I like the optimistic view that we can achieve those frame rates given the hardware we are using. So I do like that. I mean, that's probably the biggest takeaway for me in all fairness. It was just nice to also, it's just nice to have a chat and stuff. So it was, thanks for organizing that, really, Richard. Thanks for reaching out
No worries.
and stuff,
I think it's just the beginning. What we saw now is that he's somehow really interested, because what we do is more or less in the realm of his science that he did. So I think he's technically very interested in what we do, and I think it was a grand offer so that we can throw questions in the future in his direction. I think that for me is the greatest take today.
Yeah, I mean that would be. Yeah, I mean, if he's open to that sort of stuff, then I think that's got to be a win, right?
Definitely.
So yeah, it'd be great to have his experience on board. That would be awesome.
Christian, what is your feedback for today?
I wrote down some things that during our talk here, and the things are. He considers neural network to be best with detection, classification, and tracking. Tracking with, in addition to downsizing to the pixel scale. And tracking is, in his opinion, is best done with two things, the neural network and the normal regression. And he sees that background subtraction still is a very good point that can be done on both CPUs and GPUs as some kind of pre-processing. Then for neural network training, he said that actual training material is good, but should be added with simulated objects so that we can have an improvement of that and come with things that we do not know already. What have again? Okay, so the combination of simulated and real data fed to maybe self-orientating maps to find things we do not think of. The thing is, he was not very sure what is a better approach, supervised or unsupervised learning for the neural network. And yeah, according to the background stuff, he went into more the historical parts and said, okay, it is still a good point to use. And for the first phase, it's obvious that we should use it. And there are some libraries and especially CUDA stuff that might speed up this background subtraction. So we should look into the background subtraction libraries of CUDA.
Yeah.
And he was he said, just to sum it up, he said that our approach with going with a Pi 4 as a data collector and the Nano is still a good idea and might pull off what we have in mind with the hardware. So
Although
yeah,
the
and
pi
he
does-
pointed us
yes.
to the Vibe algorithm, and I think we should look into it
Yeah,
too.
absolutely. But
Yeah.
be all aware that pi doesn't have CUDA, right? So we have to be
No,
on
it's
CPU.
just used. We thought of that we're just using it as a data collector and putting everything else to the nano. And this is the idea that I presented to him, and he said it is a good idea to do it so, because the background subtraction part, there's just a few algorithms out there that use CUDA, and we do not have to use CUDA for it. And if we integrate the background subtraction part in the data reduction part, and we just so we tear it apart and give it much more room, then we could free up some performance power of the CPU from the Pi to make room for it. So yeah, he mentioned as interesting algorithms the Vibe algorithm and the Open CL, Open Computing Language. And if we can improve our pipeline with it, I think this is a go.
Yeah, and we can do the backend subscription directly on the Pi, even on a lower frame rate, because it's good enough for the neural network.
Yes.
So that's excellent also.
Well,
Yeah, so
anyway,
I'm kind of a bit. I mean, now's not the right time to get into it, but I'm a bit woolly on that approach of getting a low frame rate, like using a low frame rate and trying to then predict where an object that's moving is going to be, and all those sorts of things. So I'm kind of, now's not the right time to probably go into that, but I'm a bit. When I say woolly, I just mean I'm unsure how that works, sort of thing.
But don't forget, Mike, that you're working on a hemispheric material. It's more easier to say high frame rates for assumed scope where you just have where you just record and do not have to do anything with the material, but you have to work on the whole material on where the signal is in tiny pixels. So that's why I think I think it's a good idea to go with that, with the Pi, and to do it on the CPU only, and only with background subtraction.
Do you think? Do you guys think so? So with regards to the nano, so my concern with the nano is one of my concerns is the whole VPI library is not being maintained for the nano. So what I was thinking was maybe we should relook at the nano and specifically the VPI library, or and see what background subtraction algorithms they provide, which is supported by it's basically hardware supported sort of thing, versus we wouldn't have to. Sorry, let me just put my teeth back in and try and articulate that again. So I was wondering if we should relook at the VPI library, because it offers a background subtraction algorithm that is natively supported by the nano.
Okay.
Yes. Yeah, it does, which is natively supported by the nano, which means it won't be CPU bound. It will be run on one of the other chips. I don't know what the frame rate or what sort of frame rate it can work with, but it would be the older version of the VPI library. So it won't be the new version. I think version 2 does not support the nano, but the version before that does support the nano. So it might be that if we have to offload background subtraction onto the nano, then we should explore the VPI library again. I know that was just what I was thinking.
And regarding this low frame, I think we need at least 5. That's the bottom line for my feeling, to track some objects like birds or something and to eliminate them. Because
It
we need to
depends.
have, but for kinematic analysis, we need higher frame rates.
Yes, it would help. Absolutely. The higher the frame rate, the better it is. But the average event, when I look at videos that are recorded during the last 2 years, I see an average about 20 seconds. So the average of videos are about 20 seconds long. So that means, and these are created with a background subtraction, not with your tool, but with old SkyHub tool. And that was based on a background subtraction already. So, and what I see is we have events of 20 seconds, which is 20 frames if we go with one frame. So we have 20 frames, and from 20 frames, 20 tracks on a spline, you can do a lot. Of course, if the event is only 3 seconds, then we only have three track points, and yes, then I would also say we should go for higher frame rate.
We can do higher frame rate on the detection and the tracking, okay? But on the subtraction, we don't have to, because this is like the baseline that you can give the tracker.
But for detecting an object, we do not need 20 frames per second. 5 are enough.
Yeah. Yes.
So what we planned was that we run the capture of the image by 20 frames per second and just use ROS2 to pipe out, let's say, 5 frames per second for the tracker. Do that part, and if we detect an event, then we give the stored 20 frames per second for a reanalysis.
How do you? So isn't that a chicken and egg sort of situation? So you have to run the background subtractor on every frame to determine whether you are detecting something. You can't, you understand what I mean? So you're not going to know.
You can use the same background subtraction for the forecast of the next, let's say, 5-6 frames.
Yes.
That's what he was saying.
I'm not sure I follow, to be fair.
You do not have to do the background subtraction on each following frame. You can use the backgrounds, the master background for the next 4 to 5 frames.
Okay, yeah, okay. So in ROS2, that's quite easy to implement as well, because you can just put a timer and you can...
Exactly.
Yes.
Yeah, so... Okay. So are you saying... So currently, the way we identify an anomaly and try and track it, background subtraction is crucial to that. Because we use background subtraction to try and find the blob to then track.
And to get a signal with a signal to noise ratio above 1 sigma. To lift it up to, let's say, 3 to 5.
Yeah, so I don't... Okay, so yeah, so I'm just trying to get in my head where the tracking and all that sort of stuff's going to happen. So I suspect that's not going to happen alongside the background subtraction. I mean,
Mike, I think
now
you
it's
have
probably
to
not
think
the
in
right...
2 background subtractors. One is doing the 1 FPS on the full frame, only checking once per second, but on the full frame.
Okay.
And if it detects something, it gives the coordinate to a second one that knows the coordinate is a cropped one, a smaller one, which is higher in performance and runs on 5 or 10 frames per second, but only from a cropped part of the whole frame.
And that can be part of the neural network also, so you can parallelize it.
Yes.
Okay.
It took me also some weeks to figure it out.
Yeah,
another idea would be what should come first? First, the background subtraction of the whole frame, or should we do a segmentation first and do a background subtraction or a background analysis on the sequence? Because this would give us a more differential background subtraction, and much better mean and median values. And it is already parallelized.
Yeah.
So
I mean, doing the tiles first, it's probably a good idea for the long term anyway, because people that will have this unit, let's say 5-10 years, will be able to add additional hardware. And if we do the tile in the beginning, we will already support the parallelization.
Yeah, I have code that does frame partitioning. I was playing around with parallelizable background subtractors. And
it's actually what Tesla did also.
Okay.
It's a common approach.
So what you're all saying here is we take the raw image, the raw frames that come in, and we slice it, let's say, in 9 parts, just to have a number, and then we have 9 in parallel running BGS codes, right? Or no?
Yeah, this is what I tried.
Yes, but it's more than 9, right? Because you want to do overlay.
Okay.
Yeah.
Why do you need to overlay the things?
Because you might have object that can move from one tile to another.
Yeah, but if it exits on coordinates that are on the right edge, it will appear in the next partition on the left edge.
Yes, it's a neighboring algorithm that we provide for that.
Yeah, so probably that will be after the subtraction. You want to do the neighboring thing. Yeah.
But the neighboring is only for tracking, so that the idea is giving over.
Yeah.
Okay.
I have some sketch on my whiteboard, like modules. It goes from the frame publisher to partitioner, then to background subtraction worker manager. Then it assigns, it keeps track of the previous frame and current frame, and it distributes that between the workers that do only the background subtraction. So it's not on Git, it's on my playground, but this partitioning thing works. It's a standalone class.
And by the way, I will partition it to how many CUDA cores or whatever you have.
So for now, this partitioner runs on a single frame, thread, and it produces the partitions. Then you can distribute the partitions to many threads that are.
No, I'm speaking about like how many tiles you want to create. It's basically probably.
I was working on square frames because it's simpler that way. And when you think about our camera is like 5K by 3.6K, we just need 3.6 with times 3.6K center square crop of our sensor. And I made something that is called partitioning factor or something like that. I mean, it's stupid, I think. Wait, where is my main? It's partitioning factor. And for example, partition factor 10 means that we're going to have 10 square tiles.
Yeah, so what I'm saying is like you want to optimize here for the hardware. So if the hardware have, what it is, 1,000 cores, you probably want 1,000 tiles.
Yeah. I was also playing with Python's multiprocessing module, and there is a method to retrieve how many threads your system has. Yeah. So, but either way, it would be nice to match these two things: number of partitions and number of processing stuff.
Yeah.
So I'm confused. We're talking first about the Pi, which does not have a GPU, so and background subtraction on 1 frame per second, and you are now talking about multiple sections of the frame in parallel processed, also
because
on a CUDA core, right? Which is
my idea was
exactly. Yeah. Like we want to be able to load, right? Think about it. You're going to create a memory copy from this the RAM of the nano to the GPU, right? That has to happen. So, and you want then the thread on the GPU to start executing. right? As fast as possible. To optimize that, you want to create a tile per thread.
Yeah,
Right?
I get this.
To
Which
stream
thread
that pipe.
loads its
To
own
stream that
tile
pipe.
to the
But-
VRAM.
That has nothing to do with the pi.
I'm still confused because, first of all, we were talking about the Pi having on the full frame 1 frame per second, and you were talking about the Nano with the CUDA cores splitting the whole frame into several frames, and then processing in parallel. But isn't this in parallel already? I mean, we have the one on the Pi running on 1 frame per second. Why run the same thing but multi-threaded on the Nano at the same time? Why not only
Yeah, that's a
use
good question
parts?
because my approach was to doing background subtraction on full frame. This is why I made partitions.
Yeah, okay,
Because
that's why
I
you
wanted-
made it, Nicola. I get this.
Yeah.
This is an experiment you did, and I understand this. But when you talk further on, it gives me the feeling that this is the road
I'm
we're heading
speaking
to.
longer in the pipeline. Yes, we have a 1 frame per second that happens on the Pi.
Yeah.
That does again 1 hertz background subtraction,
Yeah.
right?
Yeah.
But we were also speaking. Maybe it's better to start first slicing to all the tiles, right, and then send them directly to the Nano, right? Now, if we have a smaller tile, the background subtraction is going to be fairly easy to execute on a small tile, right? And it can be part of the pipeline already.
And you,
But how do we know which tile is?
Now, just a second. Now, you will also. I mean, regardless of you doing a background subtraction on the Pi, you will still not want to do like a secondary version of it on a smaller tile.
True.
Where it's important, right? For accuracy, right? Because the object probably moved, in that 1 second kind of frame rate, right? So you probably want to do a secondary subtraction on the specific tile,
I see.
right?
Yeah.
Like to know exactly where the object is. So, and again, that's specifically for the neural network.
But when already the Pi knows where an object is because the background subtraction runs and when 1 hertz, then there is an event, the Pi knows it already. So it doesn't make sense to process all the rest if the Pi recognizes only one object in one particular area of the frame. So why not only process that particular part? Why process all the rest? Why do you think that it sees then more than the Pi?
Background subtraction is not a detection algorithm. Background subtraction does only reduce the data. And if we first segment the image into, let's say, 10 to 15 piles, and then run the background subtraction. Background subtraction means that you subtract values to increase the edge between the background and the event itself. And this is not a detection algorithm. Then you have to analyze this created edge.
Yeah. Okay.
And if you do the background subtraction, first do the segmentation, then do the background subtraction, and then run an analysis on the edge of the pixels, this third thing can be done much quicker on the Nano than on the Pi. So
yes.
The Nano, the Pi will just produce the data and reduce it, like bias subtraction, dark, and afterwards.
Can I imagine this result of the background subtraction like a black frame where only the objects that move are white?
This is exactly
yeah.
Yes.
Yes.
Kind of, yes.
Okay, got it. But then why do the same in parallel on the Nano again, on all the tiles? Why not only do it on the specific tiles? Or you think we missed something?
No, it's not on all the tiles. It's just optimizing the hardware execution. So you want your tile to be,
Okay, we're talking about the tile that is recognized on the Pi already, then on higher frame rate.
I said it more simple, but in reality, you want to know if the camera has 20 frames, okay, per second, and you want and you have like a 1,000 cores on the nano. Sorry, I just don't know the number, right? You want to calculate with all the frames and all of that, right? What's the fastest pipeline is going to look like? Because you want to increase the detection frame rate as much as possible. And that will need a background subtraction anyway, because you want to update the mask, like where the object is.
Yes.
Okay, so it's not really, 20 frames per second, yeah, it's a bit more complex. I need a pen and a paper to do it. My head's too old for that right now.
So
I'll send it to you. I'll write it down and I'll send it to you.
May I paint a pipeline, and maybe I'm totally wrong, but please correct me. So the Pi creates an output for the whole frame on 1 frames per second. And then from that output, we already know where the events are, and we put out these slices. And then, no? Christian, you shake your head?
No, because we do not have events yet. The event is detected later on the
but I can
nano.
easily say in the black and white
It's identified later on. Because we are talking about motion detection right now, not about identification of.
Okay, now I get it. I think I was totally on the wrong page. Sorry, guys. So what I understand now is that it's only part of the pre-process to use the background subtraction just to reduce the material. That's all.
Yeah.
Yeah, so the nano can focus
on
what's important. Yeah. Yeah.
Okay, got it now.
You reduce it on the Pi, and then you increase the frame rate and the accuracy on the nano.
That's the reason why you do this. Okay, I get it now.
Yeah.
Okay.
Yeah.
Understood. Thanks for being so patient with me.
And the reason to parallelize it, and the reason to parallelize it in per tile, so you can actually, when you have multiple objects, you will be able to still work in high frame rate without disturbing each of the tracking, right?
Yeah, true. Yeah, especially when the pre-processed material is extremely small.
Yeah, and it's not that we need to track 1,000 objects, like 5, 6 is enough, so that should be fine.
We're splitting up the workload.
Yeah, I get it.
Yes.
It's a great idea, absolutely. I mean, it's part of the pre-process. I get this now. Okay, Ido, because you were talking right now, what is your take from Pierre-Luc? What did you learn today?
Exactly this. It's kind of confirmed what Christian and me were talking about. So I'm happy to hear that we are on the right track on that.
Perfect. Thank you. I ask you just all of you, because it's good to have such feedback, because we have different brains. Nicola, what is your take today?
That background subtraction is valuable because we have a lot of small-sized objects like ISS or satellites, meteors, whatnot. So this is valuable there. For example, YOLO does not work with super tiny stuff. And I like that he also mentioned classification algorithms that take into context recent history with recurrent neural networks on LSTMs. So yeah, we're kind of on the right path. We just need to figure out the stuff and to wire it up.
I found interesting that, and I have no idea why we didn't consider it yet, that we should focus on the non-interesting part too. So to train a neural network and to recognize what is a no event, what is a no-show.
Yeah, because this helps us with reducing the data furthermore. Because if we know where there's nothing, then we can skip that part, and we reduce the workload just to where an event might happen. And this was one of the things that I found interesting too, because
like dynamic area of interest with this partitioning
yes.
or what? Yeah.
All right, then, Yannick, you want, Nicola, you want to add anything more?
Oh no, that's it.
Okay, thank you. Yannick, what is your take?
Well, I was listening carefully, and it's been a while that I was thinking about this kind of stuff. So, one thing I think was good, basically the confirmation of him that we are not in a dead end, so to speak.
Yeah.
So he exactly proposed the same approach that we were taking, I think, like this two-step approach, having the background subtraction first, and then in the second step, the neural net. And that is exactly the approach that we were developing for, right? So that I think was a good confirmation for us that it's a good approach that we were developing. And yeah, having that said from an expert in this field is, I think, is pretty good. Although there's always this confirmation bias. I mean, you always want to hear the things that, that confirm what you're doing. But I think that's exactly what he proposed. So I think that's good.
You're true. It's not biased. You're true. Yeah. I saw it the same way. Newcomer Fabio, just throw it out. What is your take?
Okay, so yeah, sure. First of all, thank you for having me also here, and I think everything here is it's amazing. An amazing thing that you guys are doing, and on the subject that we are talking today. First of all, I like his approach is most similar to yours right now. So it's the background subtraction and then machine learning. So I think that was good. And I really like his approach of doing on the Pi first. And I can say that I have tons of experience going low-level code and parallel coding. So I can try to tackle the algorithm for like his basic background subtraction on the Pi and try to optimize it further as we can on the number of cores that we have and things like this. I can try this because I can go on assembly level if needed.
Oh, wow.
And one of the things that I really liked also when he mentioned was that it's like the reverse machine learning approach. So we train the algorithm by showing him what it's not. What it's not. So when something appears that it's not, then we can pass it through. That was something I never thought about it. I always talk about it on the reverse. We train with things that we know, and then we try to identify the things that we know. And then the other approach was it means something more, I think, to us because we don't know what we are looking for. Really,
Exactly.
we have pictures or something, but we really don't know what we're looking for.
True.
So training on the reverse, I think it makes sense.
Inversion.
Yeah, it makes a lot of sense. And I think that's it. And I can help in a lot of fronts here. I just want to see where I can better fit.
Okay, perfect. Thank you very much, Fabio. And in a couple of minutes we will talk the onboarding with you. I was waiting for Pitt to show up, but he didn't make it today. So it's just you and Christian, and maybe Ido joins in if you want. But we have two people left here, and I want to get your impression. Maybe Michael, because you look so concentrated. Maybe you can give us your point of view of today.
Me?
Yes, the Michael.
Oh, okay.
The other one is Mike.
Yeah. Well. Oh, okay. Either way is fine. That's why there's a lot of mics. That's why I go by the ghost. Anyway, I did find the most interesting point that I got out of the thing was the essentially tell it what zero is, a non hit, essentially. In other words, this is nothing, and tell us when you see something that isn't nothing. You know, I found that an interesting, you know, thing to contemplate on here.
True.
So other than that, you know, I always saw the approach as sound. You know, even though I'm still getting, you know, caught up and on board with all the sordid details, and so it's you know, it sounds to me like, yeah, the project is on the right track. I do have one sidebar comment. Not exactly on track for things, but you were mentioning the like people like myself that have the stuff we bought to do SkyHub, you know, at that time, and you know, you didn't want to develop a system that invalidated that. But my take on that, just so you know, is that you know, in many ways, I consider the system that is being built to be somewhat modular, meaning, you know, I can go plug in something if I want a different kind of sensor, things like that, and make that package, you know, and integrate it in. So I don't see where, you know, where things are now and where they may or may not go is going to invalidate or, you know, basically, you know, give me a very expensive pile of junk over here on my bench. You know, to me, it's more a case of, okay, I get that up doing what it does, you know, and the system, you know, design is there. And then, you know, something else comes along and I say, oh, I want to do this. And my particular interests tend to be, well, some of my particular interests happen to be on the audio realm, you know, and subaudible and so on. And so for me to put sensors in there, there's already a provision for some of that. But if I want to get a little more elaborate, I can. But that doesn't mean, you know, I have to toss whatever I already have going on there. So, yeah. So I think that just needs to be kind of a, I don't want to put it, more or less a non-starter for an item, you know, because already people are building from what they have either out of SkyHub or like last year's spec, what the hardware list was at that point. And so I don't see where, you know, if you put up the money to do that, I don't see where you're really out, because, you know, you will still be able to use that. And then, okay, maybe you have to, you know, change out a camera or something like that. And that, you know, but I don't really see that happening either. Because, for example, I don't see any problem with running the Daiho, you know, the original fisheye camera, right alongside an all-sky. You know, right now I don't have $700 for an all-sky, but that'll change someday. So, yeah, but I don't feel out, and I don't feel it's a loss for me to have done, you know, that back equipment. And so I just want to get that comment in there.
You're absolutely right. And actually, we spoke about it last week also, Christian and me. And I mean, before even I joined, the goal was to support, you know, everything that SkyHub did, right? And the move that I recommended, and now we are doing to move to ROS 2, and think about the station as a robot, it's actually emphasizing that even more, right? And now the good part is the camera of SkyHub is actually already supported, because it's you know, it's part of the kind of video for Linux that is already there, right? So we will really have very little work to support it, right? Which is nice, right? Although, like the new camera, we actually have to implement our own driver, which is different, right?
Not really, because we wanted to make use of IndieLib and the Indie server, and that provides all the hardware we can come up with. And so because of that, we are still download compatible. And I think this is one of the things that that is a beauty of it. Because we can say, okay, if you can't afford a new camera, then go by what you have. You can use, let's say, a webcam for the start and go from there. But you won't succeed in detecting what we can detect with the suggested hardware. And for those who start with it and just want to learn about it and let's say evolve later, it's a good start to have the compatibility to video for Linux all aboard.
True.
And this is why I said it's nice to be backward compatible.
Well, like I said, I just wanted to, as in casual bystander mode, I just want to say, I think the system allows you to wherever you are, that's where you start. And if you want to add add capabilities or step up to the next thing, you can. Yeah. You don't necessarily have to. Yeah. So yes, it's whatever you're doing will have whatever results it has. And if you want to some other capability, fantastic. If you don't, then no big deal. But I just wanted to get on there, because I can see where a lot of people might worry about that.
True.
But I don't see that as really being, I don't want to say, a significant issue. Yeah. I mean, I said someday, if I were building it today, I'd just go out and buy an all-sky camera instead of Daiho, or however you pronounce their name. But, I can still run that camera because I already have it.
Yeah.
So I just want to, get that out there. And other than that, like I said, I'm still kind of mulling over what he had to say about, like I said, kind of the thing that caught my attention the most in what he said was the idea of saying, oh, this is a nothing in effect. Yeah. This is our zero or ground state. Yeah. And just tell us if something changed from that. I never really looked at machine learning algorithms that way. Yeah. It's like, okay.
It's let's say for all of us the same way. True.
Yeah. So that's my biggest remark there. Anyway, on that happy note, I'll shut up because I tend to rattle on and I know it, but that's all right.
Thank you, Michael, for rattling. No, thank you very much. Tommy, you're not a software developer, but you listen to, and maybe you have an idea. What is your feedback from today? Tommy, are you there? Okay, so I think we can skip Tommy's. Yes? No, okay. I think we have to skip Tommy. It is now 2 hours in the developer meeting, so I'd say we wrap it up for today with the recording. If there is anything anyone wants to contribute right now, please do it. Otherwise, I shut down the recording.